Let's maybe try something like this. How about? Mm, Okay. Y prime.
3 pi t.
Okay, there's something about this that's a little confusing, and I would strongly encourage you to rewrite this in a way that's makes the layers easier to see.
Everything squared.
Okay, good. Yeah, so we could write this as the quantity tangent of 3 pi t plus 2 squared. Okay, so chain rule, right? Chain rule is like an ogre, right? We said it's got they're complex. They've got layers. So what's the outside layer of this one?
The squared.
The squared. All right. So first derivative then gives us what? What is? Yeah, I've got
two hands.
yeah, I've got hand squared, and so the derivative of that is 2 hand, right? To the 1. Agreed? Okay, what's inside? Well, that's a tangent 3 pi t plus 2. Okay, next layer. We get another link in the chain. Yeah, we got a tangent then, right? Now we've got a tangent of hand. What's the derivative of tangent hand?
Secant squared.
Okay, good, good. Okay, and then the last layer?
3 pi 2 pi.
Okay, good. So the derivative of 3 pi t plus 2 is just 3 pi. Okay, and so that is our answer. What would we do with this? We could pull the 3 pi up front and get 6 pi, and then it's just tangent 3 pi t plus 2 secant squared 3 pi t plus 2. That's it. That's all we can do.
What was the score that was messing me up?
Yeah, I figured. Yeah. Okay, and that's a real common thing. Yeah, real common thing is to miss that layer. All right, I think. Yeah, I think that's probably on the first one, the only real issue. I want to look maybe real quick at second one. I know there's a couple problems on there. One in particular I want to do. Yeah, let's do one. Okay. Pretty ugly, huh?
Yeah.
Okay. Reasonably. So how are we gonna deal with this?
Put the 2 equation.
We could. We could do that. We could certainly distribute the 2 in the top if we wanted to. One thing, the fact that those are the same factors, one thing you could do here, if you wanted to, just to make this look simpler, would be to say, let's let u equal what?
2 times.
Okay, it's gonna be the factor, right?
Yeah.
So it's the factor x squared plus 3x minus 2. And if we do that, this starts to look a little better at least, right? Then we end up with y equals 2u divided by 4u squared minus 7, right? That looks a little better, right? Okay, at least we don't have to do so much writing, right? So now, what's the rule that applies there?
Can't you get rid of one of the views, or are you not allowed to?
Say it again.
Can you get rid of one of the views, or?
No, I can't because u is not a common factor of the top and the bottom. See, it's not a factor of the bottom, right? Because we're subtracting 7, right? So I can't do that. I could only eliminate it if I could factor u out of the bottom and cancel it.
So could you take the whole bottom and, or bring it to the top and make it one?
You could, yeah, you certainly could. You can always do that. You can always make a quotient into a product if you just bring it to the top. That's fine. The other alternative would be what rule? Quotient rule, right? Either one, okay? Yeah, we don't like the quotient rule. But let's just go ahead and use the quotient rule. They both would work though. So y prime then would equal what? So what's the quotient rule?
Low D high.
Low D high minus high D low. Good. Okay, so we get low times D high. Well, what's D high?
2.
Not just 2. It's 2 u prime, right? Because u prime is going to be something, right? If that were just an x prime is just 1, right? But u prime isn't. U prime is actually something. We'll go ahead and figure out what it is for now. What is u prime? Yeah, 2x plus 3. We'll plug all that stuff in later, right? So low D high minus 2u times what's D low? Now we got to use a little chain rule, don't we?
8u minus, no, 8.
8u.
7. Just
No,
concentrate.
No, we're not done though. Look at the bottom. The derivative, you're right, the derivative of 7 is 0. But the derivative of 4u squared is 8u to the 1 times the derivative of what's inside, which is a u prime. Right? Everybody see that? So I've got to have an 8u u prime.
Explain the u prime, please.
Okay, because let's just focus on taking the derivative. So all we're really doing here is taking the derivative of this, right? Okay, so the derivative with respect to x of 4u squared. How many layers are there? Well, there's actually 2, because I've got the squared layer, and then I've got the u layer. We're not taking the derivative with respect to u, right? If we were taking the derivative with respect to u, and let's do that, so you can compare and contrast here. The derivative with respect to u of 4u squared would be 8u, and then du is just 1, right? So it would just be 8u. But if we're taking the derivative with respect to x, this is different. This is going to give us, the first layer is hand squared. 4 times hand squared is 8 times hand, which is u. But then we've got to differentiate u with respect to x. Du dx is u prime, right? That's our shorthand. Our shorthand for that is u prime, right? And there's u prime right there. There's du dx, right? So yes, we did probably the smart thing, and we made this a lot easier to write and see. But think if we hadn't done that. if we had just done the straight quotient rule, we would have had low D high, which would have been complicated, times high D low. Well, when we did D low by the chain rule, I would have had to do the derivative of hand squared, right, which would have been, 8 hand to the 1 when I multiply by the 4, times the derivative of what's inside, right? I would have to include that. So that's what we call U prime. Okay? So where were we? Oh, right here. So there's the top of the quotient rule. What goes on the bottom? Just, bottom squared, whatever that is, right? So 4u squared minus 7 squared. And now we can just plug and chug, right? Is there anything I guess we could factor out like a 2u prime to make things a little easier, right? So, everybody see that? I've got a 2u prime there, and I've got 2u prime there. So I could factor out a 2u prime on the top, at least, right? And get 2u prime times what? 4u squared minus 7 minus 8u squared. Does that make sense? Right? So that's going to give me 4u squared minus 8u squared is negative 4u squared minus 7, right? Over 4u squared minus 7 squared. So that's a mess. Right. Right. And then we just would plug stuff in there. I don't even want to write it, but you get the idea, right? We could just plug in those things for u and u prime.
Wait, for the 4, how'd you get that to negative 4u squared?
Because if I'm factoring out a 2u prime from each one,
Oh, you get the, okay.
does that make sense?
How come you can just take the 2 from the U pit there?
Well, because multiplication is commutative and associative, so I'm multiplying this times this times this times this times this, but I could commute those and put the u prime up there if I wanted. Okay.
Wouldn't 12u squared be 8u squared? Wait, never mind.
Yeah, I get that minus. Okay. So anyway, that's the answer to that one. If I plug stuff in, right? It's a mess. I don't want to deal with that. I mean, we could just leave it like that if we want to, with plug the stuff in. Or if I plug it in, obviously I could. If I was really a masochist, I could square this out, and I could just multiply by -4, and then I could distribute a 2 times. I mean, it's just going to be a huge polynomial on the top and on the bottom, and maybe I could collect some like terms. That's what good's it going to do? It's ultimately we just get a bunch of x's in there, and if we want to evaluate this derivative at a value of x, we'll just plug it in, right? See what you get. Just get a number. Okay, so there's one. That was kind of nasty. And just while we're on the topic of that last ugly one, the one that you're given on the assignment, keep in mind that you're asked to find the derivative and then evaluate it at x equals 0. So are you going to want to do any simplification? Absolutely not, right? Because it's much easier to plug in x equals 0 and simplify by combining a bunch of numbers, right, than it is to do all the algebra, right? Okay. We did one of those. That. Okay. Yeah, how about this? All right. What are we gonna do? Yeah, we're gonna, good answer. Chain rule. What section are we on? Chain rule. So if I wanna find the equation of a tangent line, what do I need?
Need a slope,
Need a slope and
a point.
a point. Okay, it doesn't have to be b, but I need a point, right? So I know an x value, how do I find a y value?
Plug it in.
Plug it in. Okay, plug it in. So we get, if I plug that in, what am I gonna get? I'm gonna get secant of,
X over 4.
it would be 1/3, so pi thirds, secant of pi thirds. So this is unit circle time, right? So pi thirds takes us up there, right? The coordinates of pi thirds are what?
1/2 is
You wanna use your,
3
there you go,
pi 3 over
right?
2.
So we go, so that's right here, right? So we get 1/2, right? Square root of 1/2 and square root of 3/2.
Here's 0.
Right.
Here's 1. Here's the 3. Here's 6.
Okay.
4.
Secant is reciprocal of cosine, right? Everybody agree? So the cosine is gonna be the x coordinate, right? So it's 2, isn't it? It's reciprocal of 1/2. So we get 10 times 2 is 20?
Would it be -2?
No,
Okay,
no, just a reciprocal.
okay.
So then our point, the point is, so point is at 420. Okay, we gotta find a slope. So how do we, that looks terrible, isn't it? Soaked. So point is at 420. So how do we find the slope?
You derivative.
We differentiate using the what?
Chain
rule. So y prime equals, we just leave the 10 out front, right?
Leave the 10.
Leave the constant out front. What's the outermost layer of this?
Secant,
Secant. Derivative of secant is?
secant x, tangent x.
Secant x, tangent x. Okay, so we get 10 times secant hand, tangent hand, and hand is pi x over 12. And then next, link in the chain,
Yeah.
derivative of the angle, right? So what's that, pi over 12? And so our derivative function then looks like, if I pull that out front, I've got 10 pi over 12, so 5 pi over 6 times secant of pi x over 12 tangent of pi x over 12. So we'll evaluate that at, excuse me, 4, right? So if we evaluate that at 4, this becomes pi thirds again, right? You get back to the same angle. So the secant we already know. The secant is 2, right? So we get 5 pi over 6 times 2 times, what's tangent going to be? Tangent is going to be the ratio of sine over cosine, right? So we're going to get 1/2 divided by square root of 3/2, right?
It'd be 3. If it's sine over cosine, then it'd be square root.
Oh, other way around.
Yeah.
Yeah, sine over cosine, right. So square root of 3/2 divided by 1/2, so times 2. So it's just square root of 3, isn't it? Right? Good. So we end up with our slope equaling, what's that going to be? Oh, yikes. So we get 5 square root of 3 pi over 3. Okay, so that's the slope of the tangent line. So now it's just a matter of solving for b, right? We know the slope, we gotta find b, and so we know our point was 420. So then we could say y equals mx plus b becomes 20 equals that times 4, right? So 20 square root of 3/3 pi plus b. So what's b? Ugly. That minus that, right?
Hey, geese have feelings too.
That's true.
Be last.
So, yeah. So B equals 20 minus 20 root 3 over 3 pi, and we've got our equation. We know M and we know B,
I
right?
thought you were gonna put ugly.
Yeah. I won't discriminate. So Y equals, my slope was this, right? So there's M.
Ugly X plus ugly.
So mx plus b. That's it.
A beautiful line.
Okay. Make sense?
Sure.
All right. You guys are good. So I wanna just kind of start to introduce something different to you here. And you've got a little work to do, but this is just kind of practice work.
Score. That's the weird thing about calculus is you get really complex answers that don't feel like they should be right, but they are.
But they are.
Yeah.
Is that section 2.4?
That's 2.4 is what we just did. Yep, 2.4. Okay, so what I want to look at today, this is super cool, and I just want to start talking about this. It's going to take me a couple days to probably get to the meat of this section. But this is really, really cool. So what if we've got something like this? What if we've got something like x equals y squared, and our goal is to find y prime? Okay? What are you going to do? Right.
Figure
Write it
out,
down and then cry.
Okay, so, I mean, really, we've only got there's only one thing you could try to do here. What would that maybe be?
Square root it.
Okay, I gotta solve for y, don't I?
Yeah.
Right. So if I solve for y, what do I get here? I get y equals,
Square root.
okay,
Positive,
what's it again?
positive, negative.
Positive, negative, so plus or minus square root of x, right? If I ever take an even root of both sides of an equation, I've gotta add that plus or minus, right? And so that complicates things a little bit because now I've actually got two different functions. And you guys all get why the math gods do that? They're pretty smart. You know why they do that? They put that plus or minus in
You
there?
explained this at one point, but I
In
forgot.
physics, yeah.
They-
Because what if it's going from the other side? What if-
They do this because now think what this is. What does the graph of x equals y squared look like? It's a parabola, yeah. And what kind of parabola? Okay, I'm seeing maybe some guesses. We could find out though. You can know. You can know what it looks like because that is the inverse of what function?
Oh, it's a side graph.
Yeah, right? It's the inverse of switch the x and y. That's all an inverse is, right? The definition of an inverse sounds complicated. It's not. The definition of an inverse relation is just what you get when you switch the domain and the range. So you switch x and y. So if I switch x and y there, what does that become? Y equals x squared. We know that one well, right? So y equals x squared looks like this. Right? So its inverse has symmetry with respect to that. What is the symmetry that an inverse has, that inverse graphs of inverses have? They have reflective symmetry about what?
I have no idea.
No? You guys just not, you guys really don't know this?
Does it seem like we do? Because I don't have any clue.
Okay. This
This,
Oh,
Oh,
probably.
Stanford.
this would have been, you guys didn't talk about this in pre-calc at time?
Probably
Oh,
did, but
no.
they-
In an honors time?
well, which was what?
Especially not. We didn't even learn the unit circle like you taught us.
No, we learned the
Well,
unit.
yeah.
Okay, anyway, well, so-
Triangles.
Maybe it'll come back. I bet you did and you start remembering it. So it has symmetry with respect to the line y equals x. Okay? So we fold about the line y equals x. So then we're just gonna get, would you agree then that that's gonna end up looking like
I'm
that?
not sure. Oh, okay.
Okay, yeah.
Right.
Now
No,
it
but we
does.
never did that.
Yeah,
We never
no.
did that.
Yeah, no. That's
Okay.
like geometry.
I feel like.
No, this is not geometry. This is definitely algebra.
We dealt
This
with
is
We did
algebra.
reflections
We
in
dealt with like
geometry.
shifting
Oh,
parameters, but not
shifting,
like
I-
inverses.
Huh, okay,
We-
well, we'll do some, that's fine, we can do some review. I wanna show you a trick. Being as you haven't talked about this, I wanna show you a really good trick for finding the graph of an inverse relation. It's a little bit hard to reflect over a diagonal line. You can do it, but there's an alternate way you can do it. You can always trade one diagonal reflection over the line y equals x for 2 steps. You can rotate about the origin 90 degrees counterclockwise and then flip over the y-axis, right? You see that? So if I took the red curve and I rotated it 90 degrees, wouldn't I get that? Then I reflect over the y-axis, and that always works. And it would work for the blue one too, wouldn't it? Because if I took the blue one and I rotated up and then reflected,
So if it was a negative x squared, would it?
it's always gonna work. Always,
So when it
so,
goes
so
that
say we
way-
started off with a negative x squared, so it's down here, right? Then I would rotate it up to here, flip it over.
So you always go counterclockwise?
You always go counterclockwise, yeah.
You always flip it over the, which axis?
Why?
The y-axis. Counterclockwise 90 degrees, flip over the y. Guaranteed, always works. I've never seen that in a book, but I just know that always
100%
works.
money back?
What's that? 100% money back, yeah.
We'll knock down your door in like 30 years, be like, this, it doesn't work for this one.
No, it'll work. I know it
Years.
works. I've thought about it. I should patent that one. I've thought about it and I've kind of proved it. And it does work. It
Yeah,
really
it
is.
would be.
Our math teacher just makes everything math, math easier.
But let's get back to the math gods, because that's really what's interesting here, the math gods.
We like making ones.
What did the math gods do? They did something really smart here. When we solve for y, we break it up into 2 parts, and if you look at those 2 parts separately, let's do that. Let's split them apart. So y is equal to the square root of x, or y equals negative the square root of x. So here's positive. I'm going to go over here because this is getting kind of messy. So here is positive the square root of x, right? Y equals the square root of x. Here is minus the square root of x. Well, it's a parabola, but when we solve for y like that, even though we didn't know we were getting this, it's kind of like a baker's dozen here, we didn't know we were getting this, the answer is always given to us in terms of functions, right? This sideways parabola, taken as a whole, written as x equals y squared, is not a function. How come? Why is that not a function?
Oh, because
doesn't
the
pass
vertical
the
line
line.
test.
Yeah, it fails the vertical line test, doesn't it? Which means that there are values of x, there are input x values for which there are multiple outputs, multiple y values, right? So it doesn't pass the criterion for being a function. But if we break it into 2 separate pieces, the top half and the bottom half, independently, each one is a function, right? So the math gods are wise. They helped us out there, right? So let's take these 2 cases then. We started with x equals y squared, and we get y equals plus or minus the square root of x. So our goal is just to find y prime. Now, the whole time, that's all we were wanting to do, was find y prime. So we gotta break this into 2 parts then. We'll say, well, one y prime is gonna come from y equals the square root of x. The other one is gonna come from y equals negative the square root of x, right? Okay, so what's y prime left version? How would I rewrite square root of x?
So,
X to the 1/2, good. Okay, so then I'm gonna pull the 1/2 out front times x to the,
Negative.
yeah. So I'm gonna get 1/2 x to the minus 1/2, which is the same thing as 1 over 2 times square root of x, right? Everybody agree? Okay, on the other side, I'm gonna get y prime equals negative 1 over 2 times the square root of x, right? Everybody agree? Okay, that's inconvenient though, right? We had to solve for y explicitly before we took the derivative. Okay, is there a way that we could have maybe avoided that? Do we see a pattern here? Because sometimes it is difficult or impossible to solve for y explicitly. And when I say explicitly, that's an important word in math. An explicit equation is one that is solved for a variable. So this is explicitly solved for y. This is an implicit equation in y because the y's appear, but they're not isolated, right? So is there a way that we could have avoided the explicit process and just used the implicit equation to solve for our variable? Well, what do you think? Do you see, is there any way that I could link the derivative to the original function that I had, the original y?
The y,
So y, on the left side, y equaled the square root of x, didn't it? Well, there's a square root of x, right? So I could rewrite my result here as y prime equals 1 over 2 y, right? Right? Because isn't the square root of x just what I started with? Right? You see that? Okay. Oh, this is so cool. So cool. So on the other side, it doesn't quite look like that because my original y was a negative square root of x. But look, I've got the ingredients. There's a negative 1 and there's a square root of x. Right? So what if I just rewrote this as 1 over 2 times negative radical x? I can do that. Right? That's equal to that, isn't it? Right? So then doesn't that look like 1 over 2y? Now that's pretty powerful. Because then we end up with y prime in both cases equals 2 over y. Right? It looks like a single answer, doesn't it? So could we have gotten to there from this point without having to go through that whole process?
Derivative and then inverse.
Okay, well what if we had just differentiated using the chain rule? This is called implicit differentiation. We're not going to solve for y, we're just going to see what we get. We're going to start with x equals y squared and differentiate both sides with respect to x. What's the derivative of x with respect to x? 1. What's the derivative of y squared with respect to x? Well, that's a chain rule problem. We got 2 layers, don't we? We've got the derivative of something squared, which is 2y to the 1, right? Times the derivative of what's inside. But I'm not differentiating with respect to y. I'm differentiating with respect to x. So what's dy dx? Well, y prime, right? So by the chain rule, we're going to get a y prime there. What happens if I solve for y prime?
So 1 over y prime.
Oh, how about that? Y prime equals 1 over 2y. I've seen that before. There it is.
1 over y.
How about that?
where do you get the y prime?
Where do I get, up here? Where do we get the y prime? Okay, let's look at that.
No, where do you get the y prime equals 1 over 2y?
Because when we broke this apart, we solved for y, and we got y equals plus the square root of x, or y equals minus the square root of x. If I differentiate those with respect to x, you guys told me that the answer was y prime equals 1 over 2 times the square root of x.
So you just got it from the bottom.
Yeah,
Okay,
yeah.
just
Now,
making sure.
okay, now that way was not good. That was hard, and it could be impossible if I'd picked a harder equation to start with, right? But the important thing that we got out of this was we didn't need it, right? We got the same result here by simply just differentiating implicitly. By not worrying about isolating the y, we just differentiate everything with respect to x, and then a y prime pops out of that process. So then afterwards, we'll just solve for it, right? Super powerful. That makes that, that really enables us to do lots of problems that otherwise would be impossible or very difficult. This one wasn't very difficult, but it was more complicated, for sure, right? Okay, and then how do we interpret that? So let's look at our answer in terms of the original graph, how about? And this is probably all, when are we out of here?
15.
15. This is probably all we'll be able to get through. This is pretty good. You get to kind of see what's going on at least. So let's take our sideways parabola, x equals y squared. So we know it's going to go through the points. It's going to go through the point 1, 1, and 1, negative 1, right? Something like that. That's pretty bad, probably. You get the idea, right? So if I want to know here are the points 1, 1, and 1, negative 1. If I want to know what the derivative is at x equals 1, I can do that, right? Because I'm just starting with x equals y squared and getting the result y equals 1 over y, right? So when x equals 1, what's the y value here? 1. So this derivative then is going to be 1 over 1. So at this point, m equals 1. It's supposed to be a 2, isn't it? So it's 1/2, sorry. Everybody agree? Because at this point, when x is 1, y is 1, and so I would be plugging in a value of 1 for y. Okay, what about at this point right here? When x is 1 at this point, what's the y value? Negative 1. So if I plug in a negative 1, I find that the slope here is negative 1/2. So it works. It works even for non-functions, right? Okay? Try another one of those. This is good stuff. Try another one of these. I'm gonna give you something harder, but the math isn't really any harder. Try one like this. What if we have something like y squared minus 2y plus 3x squared equals 2x plus 4. Solve, find y prime. Find y prime. Looks like it'd be really hard. No big deal. So what do we get? If we just differentiate, take it as it is, and differentiate term by term, what's the derivative of the first term if we're differentiating with respect to x? 2y, y prime. Next term,
Minus 2y,
2y prime. Next term,
6x,
next term, next term, 0. So now it's simple. All I gotta do is just solve for y prime. The cool thing about this though, it's never gonna get very hard because how many y primes are gonna appear in each term? At the most? 1, right? To the power of 1. Right? It's always gonna end up being a part of the chain rule. And so it's just gonna pop out as being a times y prime. So it's really easy to factor. I could just, if I wanted to solve, I mean, what am I gonna do? If this were an x and these were all numbers, I would just collect all the x terms on one side and the non-x terms on the other side. So we'll do the same thing for y primes. We'll collect all the y prime terms left and the non-y prime terms right, okay? And so we get these two and then I'd have to push this guy over here, so I get a 2 minus 6x, right? I factor out a y prime on the left side. So I'm left with y prime times 2y minus 2. And then I just divide each side through by whatever's left over, right, when I factor out the y prime. And that's my answer, right?
Could you simplify it?
We could. We actually could have, probably if I had been smarter about this, way up here somewhere, we could have said, oh, well, let's just divide everything by 2, right? And that would have made that a 3 and everything else would have gone away, right? We still could. But I would say that, in my opinion, you can at the very least go right from here to the answer. Okay, once you kind of, and I would encourage you to kind of start doing this stuff internally. Because really all we're going to do, once we've separated the y prime terms on one side, the next steps are predictable, right? Wouldn't you agree that whatever's on this side becomes the numerator? And then what goes to the bottom is what I'm left with when I take the y prime away, right? So does that make sense? You can jump right to the answer from there. Okay. All right. That's probably enough math for one day, huh?